All right, hello everyone. Hope everyone is doing well today and excited for some terribly hard probability questions. So before I get started, just my philosophy on picking these questions. So all of these questions have in some version appeared in interviews. So I've just asked people I know who've done interviews at Google or financial firms as well, and they've seen some version of these problems. Hello, Brian. Also, yeah, hello everyone who who showed up. So yeah, I just want to say that some version of these problems I've seen numerous times appear in various interviews and whatnot, but also pick them because they're useful in some sense. So I've picked them because they allow yes, hello. They allow you to learn some really important, deep and interesting probability concepts. So I think as I go over the solution of these problems, the whole point is I'll be going over these concepts, and I think that's pretty much the whole point. So the first question, and I'm not even 100% sure how I want to structure this. If I want to, hello, Ken. Let me know how you feel about it. I can put the questions up and then have you guys think about it for a second. I can talk the whole time. We'll see what happens. Okay. So the first question is honestly the one I'm most excited about, the most excited to share, because it has the most math behind it. But have you guys heard of the thing where if you take a bunch of monkeys, millions and millions of monkeys, and you put them in a room randomly typing, then they will eventually type out Shakespeare? I'm sure some of you have heard that idea anyway. So here's my question to you. If you took a bunch of monkeys and you put them in a room, or let's say you took a monkey and put it in a room, and let's say it can only type letters. Okay, so it can only type letters A through Z, right? So yes, that is your rectangle. But these monkeys can type letters A through Z, and let's say each letter is typed with probability 1 over 26. So it's a uniform probability distribution. So my question to you is, how long would it take the monkeys to type "Oh, Romeo, Romeo"? Just the classic from Romeo and Juliet. So how long would it take the monkeys to type "Oh, Romeo, Romeo"? We're not case sensitive, just we'll do all caps. So how long would it take the monkeys to type "Oh, Romeo, Romeo"? Now, if you are thinking the answer is 1 over 26 to the power of the number of letters, I would say think a little bit harder. That is not the answer to the question. Okay, and if you just answer the following more basic question. Let's say you flip a coin, similar energy to this question, but let's say you flip a coin. How long before you get heads versus heads tails? Just like an easy starter problem in case you don't want to tackle the big one just yet. How many letters per second? So time is being measured just in keystrokes. So the question is, how many keystrokes would it take to type "Oh, Romeo, Romeo"? So we're just taking time out of the equation, right? So every keystroke is a 1 in 26 possibility of hitting any letter. So how many keystrokes do we expect it to take the monkey to type "Oh, Romeo, Romeo"? Okay, so just take time out of the equation. Never studied probability. We want to associate with the number. Yeah, exactly. So the probability, it's uniform. So the probability of typing any individual letter is 1 over 26 on each keystroke. Okay. And for the coins, the probability of flipping heads versus the probability of flipping tails is, a half. And so the heads versus heads tails question is, how many flips, what does it take to flip? How many flips do we expect it to take to flip heads versus how many flips to get heads tails? And the tricky thing, and I think the most counterintuitive thing for people, and the thing that I think makes these problems hard, is that it's not the same for heads versus heads tails. Okay? And so, yes, Petros, the answer is not 1/27^13. That is incorrect. Okay? So let me explain why that line of thinking is that is incorrect. And Nishant, 4 flips is correct for one of these, but incorrect for the other one. Okay, let me explain why. So think about it. Like you're flipping heads. Let's say you're flipping to get a heads, or you're flipping to get a heads tails. Okay, the reason the time is going to be different is because let's say you flip heads. Okay, let's say you flip heads. Now you are basically halfway to getting a heads tails, and you are also halfway to getting a heads, right? Now, how can it fail in either case? So let's say you flip one head, okay? Let's say you flip one head. You flip the coin again, 2 things can happen. Let's say you're looking for heads. Okay? So if you are looking for heads, let's say you flip a heads. Well, the only way that this can go wrong is if you suddenly flip a tail, right? So if you flip a tail. So the next thing you flip is a tail. Now you messed up. So you need to start over, right? So you basically need to start the process over and flip another head again in order to restart the sequence to get heads, right? Versus if you're looking for heads tails, right? Let's say you're looking for heads tails, okay? And you flip a head. Okay, cool. Same situation. You're halfway there. Now the way for you to fail is by getting a head, right? If you get a head, you have failed to get a heads tails in this situation. But notice your failure already puts you halfway to getting a heads tails. That's why these 2 numbers are going to be different. Okay, that's why it's actually a shorter amount of expected flips to get the heads tails versus the number of flips to get a heads. Because if you fail to get a heads tails by your second flip being a head, you're already halfway again to getting a heads tails. Versus if you fail to get a heads by having your second flip be a tails, you need to start over with the heads. So let me know if that makes sense. And this is what makes this a trick question. And this is what makes simple answers like 1/27 or like 27^13 flips, or like 4 flips for this one, in fact incorrect. You have to think about it a lot more carefully than that. So I'll give you guys a minute to think about this question, put it in your minds, and also let me know let me know how you guys want me to structure this, so I can start talking about the solution immediately. I can say kind of all of the problems, okay? And then talk about the solutions later. I can just talk about all the problems now, cut the stream short, and just talk about the solutions next time. I'm really not 100% sure how to structure this. Regardless, this is the question. And so in order to check your work, maybe I'll tell you the answer to the simpler question. So the expected wait time for one of these is 4, and the expected wait time for the longer one is 6. So it's 4 versus 6 for the heads versus heads tails. So that's my hint to you. That's my answer to the simpler question. So the expected wait time for a heads tails is well, I'll just say this: the shorter one is 4, the longer one will take 6. So heads takes an expected 6 flips, and heads tails takes what you might think. It takes an expected 4 flips to get. Okay. All right. So that is problem now. Brian says the way it's going now seems pretty cozy. All the problems at once would be pretty overwhelming. Okay. Mount Onso says solution now. Okay, sure, why not? So I don't know, I feel kind of bad because people have not even had a second to think about it at all. Let me do this. Let me just state the second problem, just so you can take a look at the second problem, and then we'll come back and give the solution to the first problem. Okay, so let me just state the second problem. So this is another kind of classic, famous problem. This one is a lot easier than the first one. I shouldn't say it's easy, but it's one that's generally covered in a probability class. So Marcho Markov says, O Rome equals O Rome substrings. I'm very happy that you are thinking about substrings, Mr. Markov. So keep thinking along the lines of substrings for sure. You are on the right track with this question. Okay, so let me give you another one. Maybe I was going to do a different one, but I'll go a little bit easier. So how many rolls of a die do you expect? Let's say it's a fair die, so 1 in 6 is the probability for getting any number on the die, right? So how many rolls of a die do we expect it to take to see all 6 numbers? Okay, so I'll say this about, oh my goodness, I erased the screen and I erased the box that I was supposed to use to prevent myself from covering myself. So here, let me do it like this. So how many rolls of a die, does it take on average to see all 6 numbers? I would say this is a hard probability question, but it's covered in it's covered in a lot of probability classes. So I would say this is like an artificially easy one. I think if you haven't seen this before, it's a hard problem. But the thing is, a lot of people who've taken a probability class will have seen this one before. So that makes this one kind of artificially easy. So I would say if you're struggling with the first one, I would start with this one and see how things go. And let me know if there are any questions about the problems or if you have any ideas. So just so we remember, the first question was, how long does it take to see Oh Romeo, Romeo? How long would it take a monkey? How many keystrokes would it take for a monkey to type Oh Romeo, Romeo? And then the second question is, how many rolls of a die does it take on average to see all 6 numbers? These are my questions so far. So I'm just going to wait a minute, see if you all have any thoughts about these questions. So Marcho Markov said the word substrings, which is a good thought indeed. So let's see. So GOC says 5 factorial over 6 to the 5. For the second question, no, I'm afraid that is not correct. Sorry, that's a probability. Yeah, we're thinking about how many rolls does it take on average. So my hint to you is that these are expected values. Okay, these are expected values. So as an example, the number of rolls it takes on average to see a 1 would be 6, right? If there's a 1 in 6 chance of getting a 1, then the number of rolls it would take to see a 1 would be 6. Also, I realize I slouch in my chair a lot, so I'm just going to put my camera down ever so slightly so you can see me slouch effectively. But that wouldn't consider the order, right? I think you're thinking too much about probabilities and not enough about expectations. I'll say it again. So the amount of time you would have to wait to see, let's say the number 1 would be 6 rolls because there's a 1 in 6 chance. 36. All right. Each number would require 6 rolls. Yes, that's true, but well, hold on. Once you've already seen a 1, each one is not quite independent of the other, is the problem, right? Because once you've seen a 1, it's no longer a new number, right? For example, 6 factorial? Not quite. All right. I think I'm about ready to start talking about the answers. And also maybe to think about kind of what the best way is to structure problem-solving streams. I'm still not quite sure yet. Okay, so I'm going to discuss 2 methods to solve the first question. Okay, so both of these methods are extremely interesting. I think Petros Paulos is correct, though I need to verify on a calculator what the answer is. Hold on. So it's like see. I think you are slightly off, Petros. That is not the exact number that I'm getting. But you're close to the correct answer. I feel like maybe there's some minor arithmetic error over here. So yeah, so 15.69 is not the correct answer. Okay, I want to talk about the first problem. By the way, just so you know, I have there's like 4 problems that I've thought about to talk about today, but there are 2 approaches to the first problem I would like to discuss. And this is the reason I brought the problem up, is to talk about martingales, okay? So the concept of a martingale is that if you have a fair game, let's say, like flipping a coin, let's say, or like the typewriter game, then you can't expect to win any money out of said game regardless of the strategy that you choose, okay? So what we're going to do, essentially, to solve the first problem, and I really love this, is we're going to shoehorn a game into this monkey typing scenario, okay? We're going to shoehorn a game into this monkey typing scenario, and we're going to use that game that we've kind of shoehorned in to analyze the number of strokes it would take. So the idea is that we'll kind of concoct a game to go along with our monkey typing, and the way our betting strategy will work is that we'll get a huge payout to the minute we see the monkey type "Oh Romeo, Romeo." Okay. Okay. However, the idea is that I'm not supposed to be able to win money regardless of my betting strategy. So the amount of payout I get the minute the monkey types "Oh Romeo, Romeo" should equal my losses in playing this game. Okay? That's how I'm going to choose to analyze this monkey typing scenario. Okay. The other angle I want to take with this style of problem is generating functions. Generating functions are amazing. They're like this little drop of acid you can put on math problems, and it just dissolves them many times. Generating functions are not the easiest way to analyze this particular problem, but I'm going to analyze the heads, 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 tails scenario with generating functions, just so you can see kind of how powerful the concept of a generating function is. Okay, so we're going to do two approaches, like two methods of thinking about this problem, and I just hope you learned something from the two methods of thinking about this problem. Okay, so first, let's take the Martingale approach. Okay, instead of the monkey typing, okay, I want you to pretend we are betting on the monkey. Instead of just having the monkey type, I want you to pretend that we are betting on the monkey typing. Okay? Every time the monkey types, we're going to bet $1. Okay? Now, if the monkey types what we want the monkey to type, we are going to win $26, right? Because, the monkey, like the odds that the monkey will type any individual letter is 1 in 26. So if we bet $1, we will win $26, right? So here is our betting strategy. Just so you know, the rules are, if I bet $1 and the monkey types what I am predicting the monkey will type, I win $26 off of that keystroke. Hopefully that makes perfect sense. Though let me know if that does not make sense to you. Okay, so here's my betting strategy. Okay, I'm betting $1, right? So I bet $1 on every keystroke in the hopes that the monkey will get started typing the "Oh Romeo, Romeo" string. Okay, so hopefully that makes sense. So it's a fair game, right? So every stroke we bet $1 that the monkey will type the letter O. In other words, we're betting that the monkey will get started with this process of typing "Oh Romeo, Romeo." Let me know if that makes sense. So every keystroke, I'm betting that the monkey will get started typing "Oh Romeo, Romeo." Okay. Now, let's say so by the way, because I'm betting $1 every keystroke, I'm essentially, like, $1 is leaving my pocket every single keystroke, okay? So the second rule is going to be the, I'm basically going to let it ride, right? So let's say the monkey does type an O, okay? So let's say the monkey does type an O. I just won $26. Agreed? I'm going to put all 26 back in, and I'm going to bet it on R. Okay? So the second rule is to basically, I will put my winnings back in and bet on the next letter. Okay? And bet on the next letter. Okay, so this is my betting strategy. Okay, Petros Palace is 14. The answer is 14.7. I think you're doing a computer simulation, right? You said a Monte Carlo. Okay, I'll talk about how to deal with the second problem later. Let's focus on this one. So this is my betting strategy. I'm betting $1 every time that the monkey is going to get started. Okay. Also, I have to put winnings back in. So if the monkey types in O, I take my $26 worth of winnings and I bet it on the R. Okay. I take my winnings. So let's say the monkey does type the R. Okay. In that case, I have suddenly 26 squared in winnings. Agreed? And so I'm going to put that all in again on the O. Okay? And now let's say that I get the O. Now all of a sudden I have 26 cubed in winnings, right? I'm going to put that all on the M. Okay? It's very important that you understand this betting strategy well. Also, while I'm putting my winnings back in, still every time I'm betting $1 that the monkey will type O. All right? So let me know if there's even a single question about this betting strategy, because this betting strategy will help us analyze this situation immediately. And if you ever get this question in like a programming or like a finance interview, you will annihilate this question. So let me know if the betting strategy makes sense. So I'm always, like on the side, I'm always betting $1. I'm always betting $1. And any winnings I have, I just put back in so as a bet on the next letter. Okay? So just take a minute with that betting strategy and maybe think about this question carefully. Now let me ask you guys a couple of questions. Let's say I'm sitting at the quote unquote monkey casino table or whatever. And I'm sitting here in my monkey casino table. Let's say it's been $1 million. Yes, you keep betting on O even if you win, and then you take your winnings and put that in on the next letter. Okay. So just keep in mind. So for example, if you're sitting there for like a million key presses, right? You'll lose $1 million, right? Let's say you sat there for 1 million rolls and and you did not hit O Romeo, right? And the last letter typed was like a Z. Then you lost $1 million because you bet $1 every time on an O, and whenever you have winnings, you put it on the next one. Okay. So I'm erasing the betting strategy now. So hopefully but please do ask me if there are any questions about it. Let me ask you guys a next question. What's the payout? What is the payout if the monkey types O Romeo? So how much money will you win if the monkey types in O Romeo? I'll give you guys a second to answer this one. So just to keep in mind, let's say we get the sequence O. Let's say we get the sequence O R O Z. Okay. Let's say this is what the monkey types. Okay. What are my wins and my losses? Well, I always lose $1, right? Because I bet $1 every time on the O. Agreed? You may have several betting streams going, and that is exactly the point. Okay, so I bet $1 on the first O, but I got the O, so I won $26 out of that, right? I bet $1 on getting an O again, but I got an R, but I put my winnings on the R, so my winnings at this point are 26 squared, right? And now I got an O. O is the letter following the R, so I get 26 cubed here, but notice this O also hit, so I get an additional $26 here. and then I lose all my money. I lose all my money on the Z. So for example, if you get the sequence OROZ, at this spot, your total winnings are 26 cubed plus 26, and your total losses are $3. Okay? And if you hit the Z, your total winnings are 0, and your total losses are $4. So it's a subtle betting strategy, but please let me know if it makes sense. And then, if it makes sense, tell me how much money are you cashing out with if the monkey puts in "Oh Romeo, Romeo"? And by the way, do let me know if there are any questions about why it was 26 cubed plus 26 on the third letter O. I'm more than happy to answer them. So Petrus Palace asks why. Are you asking why you have several betting streams going? I don't even know why first win is 26. So there's this is just how the betting is structured. So in order to be a fair casino, right? There's a 1 in 26 chance the monkey will type any letter, right? So if you bet $1, you should win $26 if the monkey winds up typing your letter, right? That's a fair setup, right? So for example, if you if the odds were 1 in 2, right? You bet $1, you should get $1 back. Sorry, not odds, but since the probability is 1 in 26. Okay, so why 26 cubed plus 26? Okay, I'm happy you asked. The rules, remember there are 2 rules. The 2 rules are you bet $1 every time on the monkey getting started, and then you bet, so that was rule number 1, right? You bet $1 every time on the monkey getting started with the "Oh Romeo, business, right? So that's $1 loss every time. And then if you win, you always put your winnings into the next letter, okay? So fiat every time you're betting $1 that the monkey will start the "Oh Romeo, process. Right? So if the monkey types ORO, okay, you bet $1 on the O. Agreed? And the monkey typed the O. So you win $26 off of the first bet. Agreed? On the next turn, remember, you're always betting $1 on the O, but you always put your winnings on the next letter. That's exactly right. Also, Ken Haley, you're off because the last letter is an O. You're very close to the correct answer, though. Okay. So, you put your $1 in on the first O, you win 26, but then you put your winnings on the next letter. You put the winnings on the R, so you get 26 squared, because you put all $26 on the next letter, which is an R, which hit, so now you have 26 squared dollars, but you also lose some money because you're always betting that $1 on the O getting started. Right? Now, the next letter after the R is an O, so you take all your winnings from the R and put it in the O. So at this point, you'll have 26 cubed from hitting the O, but you also lost the $1 because you bet the $1 on an O. But wait a second, the O hit. So it's 26 cubed plus 26 for ORO. You just fixed it, Ken. That's absolutely correct. Okay. So Let me know, Petros or anyone else, if you have any, if it makes sense now, why you would be, why your winnings would be standing at 26 cube plus 26 at ORO, and your losses would be $3 with this betting strategy. Okay, I assume it makes sense. I hope it makes sense. And Ken in the chat said your winnings at the end of an O Romeo Romeo would be 26 to the 13 plus 26 to the 6 plus 26, which is correct. The payout from putting your winnings back over and over and over again would be 26 to the 13, but then you started a new betting stream on this O, which resulted in a Romeo, which gives you 26 to the 6, and then you also won again on the O, which gives you a 26. Okay? So let's say this is your betting strategy. Your betting strategy is, I will leave the casino the minute I hit O Romeo, Romeo. Okay? So if you wait at this casino, let's say you wait as long as it takes to hit O Romeo, Romeo, and then you hit it, this is what your winnings will be. Agreed? But because this game is fair, your winnings must equal your losses. Once again, so I'm not going into like the technical details of it, but if you play in a fair game, no matter what strategy you choose, you cannot expect to make money from a fair game. So your expected winnings should equal your expected losses, okay? So you win, your winnings are 26 to the 13 plus 26 to the 6 plus 26. But what are your expected losses in this situation? Your losses are, well, you bet $1 every keystroke, right? So your losses are precisely the number of keystrokes. So we get 26 to the 13 plus 26 to the 6 plus 26 minus the number of keystrokes has to equal 0. So the number of keystrokes is precisely 26 to the 13 plus 26 to the 6 plus 26. How about that? So this is an amazing way to answer this type of interview question. Let me know if there are any questions about it. Means the same number of, exactly. So the expected number of time it'll take for the expected number of keystrokes it'll take for the monkey to type out "Oh Romeo, oh Romeo" is precisely this much, because your expected your net revenue from this process has to be 0. You lose $1 every turn, and if you walk away the minute you hit "Oh Romeo, Romeo," remember your expected revenue from this game has to be 0. You lose $1 every keystroke. You win this much if you hit the "Oh Romeo, Romeo," and so the expected amount of time it takes to hit "Oh Romeo, Romeo" is precisely this much, which I think is amazing, to be honest. You try it any other way, you'll be extremely miserable, I swear, doing this problem. But in any case, let me know if there are any questions about that. Okay, so I'm very happy that I got to share this whole business of martingales with you guys because it is so amazing. Let's do the heads, tails situation with the same betting strategy. Let me know how long it would take. The same idea. So if you're flipping heads, tails, the payout should be 1 and 2 now, right? Because that's what would be fair. If you're flipping a fair coin, right? So what's the expected wait time, or well, what's the expected number of flips it takes to get a heads tails versus a heads? So let's do the exact same betting strategy type analysis. So I'm going to put in $1 every time on the heads tails getting started, right? Could you say what is the basis of assuming a fair game in equals out? So there's a big theorem. I'm not going into the technical details of it, but the theorem is if you play a fair game, then regardless of the strategy you choose, right? Regardless of the strategy you choose, your expected earnings from this game should be 0. Okay? It's sort of like, let's say you flip a fair coin, and you put in you get back your money, like you win like $2 every time you're right about flipping a fair coin. You can come up with whatever elaborate strategy you choose to make money off of flipping a fair coin. The point is you're not gonna make any. Long run average, you're not going to make money on such a game. Okay? If you play a fair game, your expected earnings ought to be 0. This is at the heart of understanding, or this is like at the heart of the theory of Martingale's. I hope that at least makes intuitive sense. But you can, of course, just look up Martingale if you want to see like the theory of it. I'm not sure if it's particularly appropriate or relevant for this stream. But I've given you the keyword now if you want to dig deeper here. Anyways, I hope that gives you some idea or at least intuition for your question. Okay. So in the heads tails analysis, what do you walk away with if you hit heads tails? Well, you walk away with 2 squared plus 2. Oh, I'm sorry, I'm messing up. In the heads tails, you walk away with 2 squared, right? In the heads scenario, you walk away with 2 squared plus 2, and the additional 2 comes from the fact that you're betting $1 every time, right? So you would lose an additional $1. You would win an additional $2 when the second head hit. So it's actually an expected 6 flips to get the heads and only 4 flips to get the heads tails. Okay, so I wanted to spend like a brief moment talking about, what would you do if you did not know about martingales? How would you analyze this question in a conventional way? And the answer to that would be you would have to use generating functions or something along those lines to analyze it. But before I dive into those, I should at least give you guys the answer to the second question. How many rolls of a die does it take in order to see all the numbers? What's the expected number of rolls that it takes to see all of the numbers? Okay. Just let me know if any of you would like more time to think about that question, but if no one says anything, I'm just going to give the answer right away. Just so you know, the first time in my life someone explained to me that like heads tails and heads don't have the same expected wait time, I was a little shocked as well. Like it did not make intuitive sense to me for a little bit. But I think analyzing the substrings really helps because you realize that with some strings, even if you fail, you might be on the way, like you might be further along the road to succeeding. Versus with other strings, the minute you fail, you're in bad shape. You need to start over from scratch. And that's what affects the different wait times for things. Like fundamentally, that's what's going on. And the Martingale analysis kind of perfectly captures that. Okay, so now I'm going to talk about this thing with the die. Okay, so the principle that I wanted to illustrate with the... can you get this with Martingale analysis? I'm not sure. Maybe. But there's actually a different principle that I wanted to illustrate with this one, which is linearity of expectation. How many of you have heard of this before? So just so you know, just like martingales are like a very powerful strategy to do probability questions, this one is also, like a hot knife into butter for a lot of questions. Like it just makes analysis of a lot of different types of questions. Extremely, extremely easy. What is at the heart of linearity of expectation? Well, at the heart of the linearity of expectation is the idea that expectations are linear. So I'm not being facetious. So the idea is that in life you might see many random variables, okay? And analyzing probabilities with random variables can be extremely difficult, okay? But if you're interested in an expectation, so if you're interested in an expected wait time, a probabilistic average, or something along those lines, right? So if your probability question has the word average in it, you should be very suspicious that you might be able to use some linearity of expectation type shenanigan, okay? So the idea of linearity of expectation is very similar, which is very simple, which is, let's say I have two random quantities, x and y. The expected value, or the average value, however you want to think about it, the probabilistic average of x plus y splits as the expected value of x plus the expected value of y. Why? Because these are averages. Okay? So the justification for this is that these are fundamentally averages. Okay? So, this is true even if your random variables are not independent, okay? Very important here. In fact, that's a huge part of what makes this so useful. Hold on, I have a new message. So what I understand, the always bet O, I think O, 26R, 26 squared. That's a lot to read, but I think hold on. Hitoshi sent a message. Let's see. So E. I think you might have like a typo at the very end there, but it seems otherwise correct to me. Just remember, the betting strategy is you always bet on the monkey getting started, and anytime you win something, you put it on the next letter. Okay. Linearity of expectation is the idea that averages always break down this way, and they break down this way regardless of whether or not x and y are independent. Okay? So this is really important. So this is true whether or not x and y are independent. Okay. So let's use this to analyze how long it would take to see all 6 numbers on a die. So, all right, let's start with an easy question. Let's say I'm going to call x is going to be my random quantity, okay? And this random quantity is going to be, let's see. So this is the number of rolls to see all 6 numbers on a die. Okay, this is my random quantity. Okay. So x is the number of rolls to see all 6 numbers on a die. Okay, hopefully I'm not saying anything crazy right now. Here's what I'm going to do. I'm going to split x as follows. So x is, I can split it like this. I can split it as the number of rolls to see first new number. By the way, this is going to be 1, right? The expectation for the number of, like the expected amount of time to see a new number is 1, because every number you roll on the first roll will be new, right? Plus the number of rolls to see second new number. Okay? And so on, all the way down to the number of rolls to see the sixth new number. These are all random variables. In other words, all of these are random quantities. Okay? Every single one of these is a random quantity. And I hope you accept that the number of rolls to see all 6 numbers on a die really is the sum of these 6 distinct random quantities. Okay. Also, I want you to note that these random quantities are very much not independent of each other, right? So, right, they're all very, very deeply interconnected. They're all very dependent on one another, right? However, the neat thing is you can break things down with expected values. So as long as I can write a relationship between random quantities, that's like x is the sum of these 6 random quantities, it will always be the case that the expected value of x, or the average value of x, right, is going to break down as a sum of the expected values for each of these 6 quantities. So this will be, you know, the expected number of rolls to see first new number, right? Plus the expected number of rolls to see second new number, and so on, all the way down to the expected number of rolls to see the 6th new number. All right, let me know if there are any questions about this. Hopefully everything I've done so far is making sense. So even though these are not independent quantities, this will break down in expectation. Okay? So let me just ask, what is the expected number of rolls to see the first new number? Well, that's just 1, right? Hopefully I'm not blowing anyone's mind here. Every number you roll is new when you roll a die. And J55 got it. That is the exact answer. So it's just going to be 1 plus the number of rolls to see the second new number is, well, how many numbers on the die are new at this point? How many are old at this point? Well, there's 1 old number, and there's 5 out of 6 new numbers. So it'll be 1 over 5 over 6, and then 1 over 4 over 6, and so on, right? All the way to 1 over 6, which is just okay. Hopefully that makes sense. So it's just going to be 1 plus 6 over 5 plus 6 over 4 all the way to 6, which I believe is 14.7. So I think Petros got very close. I believe Petros is doing a Monte Carlo simulation. So this is going to be about 14. This is I believe 14.7. Did this earlier, so it should be 14.7. Let me know if there are any questions about this. Linearity of expectation is a lovely, lovely tactic that you can use to solve all sorts of difficult to analyze problems. And the idea is very simple. You have something that's very challenging to compute, and you break it down into quantities that are easier to analyze, and you don't even need to worry about whether they're independent or not. The expected values will break down linearly regardless. Okay, it's very interesting. Very, very interesting indeed. So this was an interview question, by the way, at like a major financial firm. I won't say which one because I am bound not to. But there you go. There you have it. Let's do another one. Also, let me know about the level. Would you guys like me to go for harder problems than the ones we've discussed so far, or easier problems than the ones we've discussed so far? I can also just keep. I'd initially want to simulate, but it seems much simpler. Yeah. I think some people in chat were simulating these, but regardless. Okay, well, let me just do another one. Okay. Here's the question. This is a famous question. It's a famous like probability riddle. Here's the game. You and I have a team of gladiators. Okay, same number of gladiators. Okay, we are both emperors. I don't know if there was ever a time where there were two like emperors of an empire, but you and I both have a team of gladiators, and these gladiators have various strengths. Okay, so I'm gonna indicate the strength of our gladiators by let's just do whole numbers. Why not? You can do any real number, but it doesn't really matter for this question. So let's say my 10 gladiators have strengths like 1, 2, 17, 36. That one's really strong. And let's say 1, 7. I'm just writing numbers at this point, so I'll stop. Let's say this is my team of gladiators. Okay. You got 1, 2. You got 1 of strength 1, 1 of strength 2, 1 of strength 17, 1 of strength 36, 1 of strength 1, 1 of strength 7, 1 of strength 9. Okay, these are my gladiators. Okay, these are the strengths of these gladiators. Okay, you also have a team of gladiators. Let's say, and they have their own strengths. So maybe 2, 7, 50, 31, 6, 3. Okay, we should have the same number: 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6. Okay, I'll just throw another one on. Okay, so I have my team of gladiators, and you have your team of gladiators, and this is a list of their strengths. Okay, here's what we're gonna do. We're gonna have a matchup. Okay, we get to decide who goes up to compete first. Okay, so it's a pretty simple idea. We're trying to decide who goes up to compete first, and let's say I send out my gladiator with strength 17, okay? And you send out your gladiator with strength 7, okay? Yeah, that gladiator is super strong. Okay, here's how the probabilities work, okay? So I send out my gladiator with strength 17. You send out your gladiator with strength 7. My gladiator will win with probability 17 over 24. 24 is just the sum of 17 and 7, right? And your gladiator will win with probability 7 out of 24. Okay? Hopefully that makes sense. A caveat is if your gladiator wins, right, then the strength of the losing gladiator is added to the strength of the winning gladiator. Okay? So, hold on just one second. Okay, yeah. I've said it correctly. I was rechecking the problem. By the way, this particular problem is from this book, Mathematical Puzzles, a Connoisseur's Collection. It's a lovely book. I recommend it. It's by Peter Winkler, in case you want to look it up. So I was just reading. I just want to make sure I wasn't messing it up. There's a couple of really good books. I can give you guys recommendations. So there's another book called 50 Challenging Problems in Probability. Another one of my problems came from there. So I just put it up here. 50 challenging problems in probability. And I got like one of the other problems from a finance book as well. I have like a bunch of problems to go over, but I'm probably not going to get through them today. But okay. So your Gladiator will win with probability 17 out of 24. A bit behind, but the method was similar to finding the probability of a row, 6 distinct rolls, but adding the inverses number of rolls, right? Well, it boiled down to linearity of expectation. I'm afraid you might have to rewatch to figure out what was going on. But I'm sorry, I keep getting distracted. But the probability that my Gladiator will win is 17 out of 24, and the probability that your Gladiator will win is 7 out of 24. And if mine wins, then its new strength is 24. So I inherit the strength of the losing Gladiator. So let's say I win, then your Gladiator's dead, and my new one has a strength of 24. So here's my question to you. The player who wins is the one with a living Gladiator at the end. Okay? So my question to you seems like a pretty useful question. What strategy do you want to use here? I'll give you guys a minute to think about this. What strategy do you want to use? You know, you could decide like, oh, I want to put the strongest one up first. Or you could be like, oh, I want to put the weakest Gladiator up first, right? It's up to you. You can do whatever you want. You can analyze it mathematically. Oh, see you later, Ken. You can analyze mathematically, you know, however you choose. But you can also just tell me intuitively what you would do. So J55 says hunch is the strongest first. Okay, it's a good hunch. This was my hunch as well, I'll say. Let me know if anyone else has any intuition about what they would do. Just to guess, like if you were just guessing, what would you do first? Use tit for tat. If they send out their strong guy, then send out your strong guy the next time. Otherwise, use your weak guys. Okay. Okay. That's an idea. I'll take one more idea and then I'll reveal the answer. Or if no one wants to say, that's fine as well. Both emperors know both rosters, and I do believe you can fight one more than once. If you couldn't fight a gladiator more than once, then the strength of the gladiator improving would be meaningless, right? Like it wouldn't really matter that the strength of the gladiator went up to 24. Oh, I'm sorry. There was another suggestion. Hitoshi says the opposite seems to send the strongest, then the weakest. Okay, I have some very interesting news for you guys. It turns out this is strategy independent. We got another weird situation on our hands. Regardless of what strategy you use, there's no strategy that can change the probability of the outcome. Okay? I know this is extremely shocking, but it turns out it truly does not matter what strategy you use. You cannot change the probability of the final outcome. Now, I'm reaching an hour, so I might have to assign this to you guys. Well, it's like homework, but I'll just talk about it next stream. So I'm streaming again on Wednesday at 1 p.m. But the answer to this question is that it really does not matter. The strategy absolutely does not matter. But I want you guys to think about it. And if you don't feel like thinking about it, you can computer simulate it as well. You know, just make a little simulation and see what happens. Both can be a lot of fun. A lot of fun. If you like, I can give you another question before you go. This is kind of interesting. And we'll talk about this one. So I already gave you the answer to this one, but let me give you another one. But this is another really famous interview problem. It's pretty interesting. So I was thinking that until you said the absorption thing, which put me off. I didn't mean to be misleading. I do think the problem itself is a little misleading. But anyways, I did not mean to be misleading. Let me just spend like a minute giving you guys another question, and we can talk about both of these questions next time. So feel free to take a shot at proving that the order of your gladiators absolutely does not matter. And then I have another one for you, which is kind of interesting. Let's see. It's just a matter of sum of what numbers you have. That's true, but you have to prove it, right? Or simulate. I don't know. Do whatever you like to justify it to yourself. I have to say, when I first saw the problem, I found it extremely counterintuitive. But before I go, I'll leave you with one more problem. So this is I guess this would be problem 4 of our brutal probability set. Okay. So number 4 is the following problem. So we're playing a game, and the game's very simple. We're just going to flip a coin. Okay? Very simple. So the game is flip a coin. If it lands heads, I win. If it lands tails, you win. Okay? So flip a coin. If the coin lands heads, I win. If the coin lands tails, you win. Okay. A few more conditions. I'm going to flip the coin an even number of times. Okay, that's one caveat: an even number of times. Okay, so I'm flipping the coin an even number of times. Okay. Also, I'm going to say, let's say the probability of heads is 0.4. Okay. Hopefully this game so far makes sense. So I flip a coin an even number of times. Heads I win, tails you win. 0.4 is the probability of landing heads. So this game, yeah, I know, heads I win, tails you lose. So this game is against me. Agreed? So this game is not in my favor, because the probability of heads is less than a half. Okay? So, to win overall, right, to win overall, I have to win more than half the games, right? I have to win more than I lose, right? I have to win more than I lose, right? So no ties, A tie, I lose. Okay? Tie, I lose. I have to win more than I lose. Okay? To win overall, I have to win more than I lose. Okay? So here's my question to you. Let's say I have an option of how many times the coin is flipped. So I can choose that the coin be flipped twice, or 4 times, or 6 times, or 8 times, or 10 times, or 12 times. How many should I sign up for in order to maximize my probability of winning overall? So I get to choose the total number of flips, as long as it's even, right? How many should I pick? That's my question to you. Phoenix Fire says 2. Okay. Any other guesses? So Jamie says -2, therefore. Yeah, so so to Phoenix's guess, that was the same as my guess when I first saw this problem. It seems like if the odds are stacked against you, if the odds are not in your favor, you should play as little as possible, right? That seems to be the intuitive thing. But it's not correct here. So first of all, I want you to think about what the correct answer is. And then if you find that too easy, analyze the situation for any p less than 1/2. Okay? So at what point is it favorable for me to play 2 games? And at what point is it favorable for me to play more than 2 games? That's your challenge question, I guess, if you find this one too easy. Just keep that in mind. So it's not that hard to think through. Okay, this is a famous interview question. So I hope you guys enjoyed all these. 2 sounds like variance plays most in your favor, but given the context, I guess it doesn't actually matter. I'm not sure how to think about this in terms of variance, to be honest with you. But yeah, I encourage you to write out the probabilities and just see what happens. It's kind of curious what happens. I will say, I said this earlier, but all of the strength of my intuition went towards saying no, if the odds aren't in your favor, you should play as little as possible in order to maximize your chances of winning overall. But there's something kind of weird going on here, which we can discuss potentially next time. Okay, many of you have recommended that I don't talk for too long because math capacity is only so high. So I hope you enjoyed these problems. I really love the Martingale one. That's definitely my absolute favorite. Though there's something interesting going on with all of these, and I'm very excited to share them all with you. So join me again on Wednesday for my next stream. It'll be again at 1 p.m. Eastern time. And thank you all. Thank you to everyone who showed up. That's all out of me. And I'll talk about these 2 problems next time. But, yep, that's it. Peace.